What's the largest volcanic eruption you have ever heard of? Is it Mount St. Helens, Tambora, Krakatoa, even Yellowstone? All of these pale in comparison to the strongest and largest eruptions in Earth's history. They're called large igneous provinces and are extremely powerful and rare. In this video, we will discuss the smallest and largest, their rarity, and the destruction and ecological effects they have on planet Earth. Get ready, as it is about to get a bit hotter in here. Large igneous provinces represent some of the most dramatic, landscape reshaping events in Earth's history. Unlike ordinary volcanic eruptions that build mountains or islands over long periods, these unleash mind-bending volumes of magma across continents or ocean floors within geologically short intervals. These immense outpourings occur when deep mantle plumes rise and decompress, releasing extraordinary amounts of molten rock. The scale is staggering. Many involve over 1 million cubic kilometers of lava. That's enough to bury entire regions beneath layers hundreds of meters thick. Such eruptions don't behave like typical volcanoes. Instead of forming steep cones, they create vast, flat plateaus known as flood basalts. Lava pours from long fissures rather than single vents, spreading in sheets that can travel hundreds of miles before cooling. The most famous example is the Siberian Traps, a cataclysmic large igneous province that erupted about 252 million years ago. Its eruptions were so prolonged and so massive that they triggered the most severe extinction event in Earth's history, wiping out more than 90% of marine species and 70% of land species, several times. Another enormous one is the Deccan Traps of India. Formed around 66 million years ago, its volcanic activity coincided with the mass extinction that ended the reign of the dinosaurs. While the asteroid impact was the final blow, the Deccan eruptions had already destabilized ecosystems across the planet. Large igneous provinces release staggering amounts of gases into the atmosphere, including carbon dioxide, sulfur dioxide, methane, and halogens. These gases alter climate systems at global scales. Some drive intense warming, while others trigger sulfur-driven cooling episodes, leading to glaciations or wild climate swings. The initial stages of these events are often dominated by explosive degassing. Magma rising rapidly from deep sources brings volatile compounds to the surface, which expand violently as pressure drops. These explosions can inject vast plumes into the stratosphere, disrupting climate for decades. As eruptions continue, enormous lava flows spread across landscapes like molten oceans. Some flows remain fluid for months or even years, enabling them to travel incredible distances. These flows drown valleys, bury forests, and reshape river systems, leaving behind thick basalt layers. One of the most striking features of a large igneous eruption is its longevity. Even though their main eruptive phases may occur over 1 or 2 million years, this is still extremely short compared to their entire life. Yet the environmental consequences can last tens of millions of years as ecosystems recover. Scientists investigate these not just for their geological significance, but for their deep influence on life. Nearly every major mass extinction in the past 500 million years aligns with a large igneous event. This connection makes them crucial to understanding how planetary systems can collapse under extreme stress. The volcanic gases released during such events can acidify oceans, disrupt food webs, and lead to anoxic zones where oxygen disappears entirely. Marine ecosystems are especially vulnerable because small changes in temperature or chemistry can cascade through entire biological networks. On land, they can devastate habitats by eliminating forests, drying out wetlands, and altering rainfall patterns. The long-term warming produced by high carbon dioxide levels can transform climate belts, pushing biomes toward the poles and shrinking available ecological niches. Another dramatic effect comes from mercury emissions. Large igneous provinces release massive amounts of mercury vapor, which settles into soils and water bodies. This toxin accumulates in organisms, causing biological stress and contributing to extinction pressures across multiple environments. Oceanic ones, such as the Ontong Java Plateau, reveal another dimension of their power. These underwater eruptions create vast basalt provinces on the seafloor. They can disrupt ocean circulation, generate intense hydrothermal systems, and even alter the chemistry of entire ocean basins. The heat released by these submarine eruptions can cause thermal expansion of seawater, altering sea levels. Meanwhile, the release of dissolved metals and nutrients can spark blooms of microorganisms, which sometimes lead to widespread depletion of oxygen at depth. The largest igneous province eruption ever was the Ontong Java Plateau, an underwater giant forged around 122 million years ago. Unlike continental events, which erupt in massive lava floods across land, the Ontong Java event took place beneath the Pacific Ocean. Even so, its scale is staggering. While the Siberian Traps unleashed around 7-8 million cubic kilometers of lava, and the Deccan Traps produced roughly 1 to 2 million cubic kilometers, the Ontong Java Plateau erupted an almost unthinkable 50 million cubic kilometers of molten rock. That makes it 6 to 7 times larger than the Siberian traps and 20 to 50 times larger than the Deccan traps. This formed a submarine plateau the size of Alaska and several kilometers thick. It is so massive that it accounts for nearly 1% of Earth's entire crustal volume. Because it erupted underwater, the Ontong Java event didn't produce towering ash clouds or global firestorms. Instead, its eruptions created immense networks of underwater lava flows that cooled quickly into bulbous formations known as pillow basalts. As these flows spread across the seafloor, they drastically altered ocean circulation patterns and displaced enormous volumes of water, potentially generating tsunamis and localized ocean upheavals on a scale that has never been observed in history. But the real impact came from chemistry, not lava. As the Ontong Java plateau formed, it unleashed massive amounts of dissolved metals, heat, and volcanic gases into the ocean. These inputs fueled the explosive growth of microorganisms, resulting in massive algae blooms that consumed oxygen as they decayed. The result was widespread oceanic anoxia, a deadly loss of oxygen that suffocated marine life across vast regions of the Pacific. Researchers even linked this event to a global oceanic anoxic event, a period when large parts of Earth's oceans turned into stagnant, toxic basins. But not all flood events are catastrophic. Some are subtle, yet still immense. The smallest events, while minor compared to the Siberian or Deccan traps, still unleash thousands of cubic kilometers of lava over tens of thousands of years. Timing is everything. They erupt in pulses that can last a few thousand years to a couple of million. In geological terms, that's the blink of an eye. Mantle plumes rise slowly over tens of millions of years, storing heat and pressure until the moment the crust can no longer contain it. Then, suddenly, the flood begins. In some regions, flows are stacked hundreds of meters deep, forming plateaus so massive that they can be seen from space. The Siberian traps alone covered more than 7 million square kilometers at their peak. The gases released are equally staggering. Carbon dioxide floods the atmosphere, raising temperatures globally over thousands of years. Sulfur compounds form dense aerosols, reflecting sunlight and plunging climates into temporary ice ages. Methane and halogens amplify these swings, creating an unstable climate roller coaster that can last for millennia. Marine ecosystems feel the first punches. Ocean acidification weakens shells, disrupts food webs, and triggers anoxia, zones of zero oxygen where nothing can survive. Entire species vanish from the fossil record in what seem like sudden collapses, though in reality, these crises unfold over thousands of years. Lapses rewrite the blueprint of life in oceans. But here's the good news. Large igneous provinces do not erupt suddenly. They are the result of titanic forces building beneath the surface for tens of millions of years. The process begins deep within the mantle, where the temperature and pressure are extreme enough to create buoyant plumes, columns of superheated rock slowly rising toward the surface. These plumes ascend at just a few centimeters per year. Even at that pace, it takes 10 to 50 million years for a plume to travel from the core mantle boundary to the base of Earth's crust. But reaching the crust is only the beginning. Before a single eruption happens, the plume head spreads outward like a mushroom, pushing against the underside of the lithosphere. This hot, swollen plume can become 500 to 1,000 kilometers wide, and as it presses upward, it begins to weaken the crust above it. Over the next hundreds of thousands to millions of years, the crust uplifts, fractures, and stretches. This creates long fissures and rifts where magma will eventually escape. When these ingredients come together, the stage is set for an eruption. But even then, the transition from primed plume to global catastrophe is not fast. It takes thousands to tens of thousands of years of escalating volcanic activity. Small fissure eruptions appear first, releasing gas and heat. Dike swarms spread through the crust. Magma chambers grow and merge, storing volumes that eventually reach millions of cubic kilometers. Only after this long buildup does the main eruptive phase begin. And even that main phase is not instantaneous. The thickest, most violent pulses of the event take place over 500,000 to 100,000 years. These are the intervals when lava floods continents, oceans turn anoxic, and global climate spirals into chaos. Ultimately, these events are not singular eruptions, but an era of volcanism that alters life on Earth for tens of millions of years afterward. In the end, large igneous provinces are reminders that Earth's interior isn't quiet, it's patient. A mantle plume can spend tens of millions of years rising through the mantle, hidden and silent, waiting for just the right tectonic weakness to pierce the crust. But they also show us the deep rhythm of Earth's geology. These events don't happen randomly or frequently. They require immense buildup, unique tectonic settings, and precise timing between plumehead expansion and lithospheric stretching. And because of that, they're as rare as they are catastrophic. So as we study places like the Ontong Java Plateau, the Deccan Traps, the Siberian Traps, and other silent scars of ancient fire, we're not just looking into the past. We're learning how alive a planet can be, and how profoundly it can change when the Earth decides to breathe out. Hey everyone, thanks for watching my video. I hope you enjoyed it. Since this is my first video, you may have noticed a lot of audio cuts. I'm working on that, but I did make mistakes during the recordings. I promise to improve for the next video. If you like this content and want to see more, hopefully with better quality, please like and subscribe. I'll be reading your comments and trying to create a video based on your suggestions. I'll also work on fixing my microphone for the next upload. Thanks again, and I hope you enjoyed. Until next time.